I'm going to talk about the importance of wall slip in practice of rubber processing and how to measure. Sorry. Okay, so in rubber compound processing is now often analyzed by modern flow simulation computer application. The prediction of injection molding parameters, extrusion output, and shape require precise knowledge of the material flow properties. That implies the variation or the knowledge of the true viscosity as a function of shear rate and temperature. The measurement of true viscosity is somewhat difficult to apprehend, but it's a prerequisite for successful simulation. The most used instrument for measuring rubber compound processing characteristics remains in the world the capillary rheometer. But this popular instrument nevertheless requires numerous corrections involving multiple tests before providing the true viscosity of the material of interest. Now, what I'm going to try to do is to show you that we can use a closed boundary biconical rheometer. Everyone knows that machine as RPA, which is an interesting alternative to capillary rheometer for the measurement of steady flow viscosity and wall slip. Okay, so in capillary rheometer, as we have seen, we need to perform a series of correction, and this is due to the fact that all the equations which are used are based on Hagen-Poiseuille equation for Newtonian fluid. Now we have the graph of the capillary rheometer. We can see that it is based on the measurement of the difference in pressure between the entrance and the exit of a die. Now, we can see from that diagram that actually the pressure sensor is a little bit higher than the entrance of the capillary. Therefore, it introduces an error. So the pressure which is used to measure the shear stress needs to be corrected for entrance. For true shear stress. Also, we know that we are dealing with non-Newtonian material, so we need also to correct for shear rate, taking into account the non-Newtonian material behavior. There is other things which are really important when we consider measuring viscosity of material in a capillary rheometer. It assumes no wall slip. That is, of course, a big problem in testing rubber compound. Another one is very little or negligible viscous eating, which is not really true as well. And there is no pressure dependency of viscosity. That is absolutely untrue as well, depending on the formulation, because there exists some free volume in polymers. So very briefly, the basic two corrections, which are the Bagley and Rabinovich corrections. The first one is to correct, as I said, the entrance pressure effect. So we normally measure delta P, which is the difference in pressure, and the shear stress is derived from that pressure. Now, as we have an extra pressure from the entrance, we need to remove it, and this is called, therefore, Bagley correction. This requires normally 3 tests, or at least 2 tests with different L/R dies, or 3 tests if we want to look for non-linear Bagley plot. In this case, we can see that if we extrapolate to 0 L/R, we measure P0. This nonlinear response indicates a small but significant compressibility effect. The second one is the apparent viscosity correction for non-Newtonian behavior called Rabinovich correction. And in this case, the apparent shear rate is equal to 4 times the output of the capillary divided by pi r cube, r being the diameter, sorry, the radius of the die. And for the correction, it has to be multiplied by 3n plus 1 divided by 4n N being actually the slope of the log shear stress divided by the log shear rate. And the ratio of the corrected shear stress by the corrected shear rate is theoretically giving the corrected viscosity. But this requires wall slip correction if necessary. Okay, why bother about wall slip? Well, this is an extract from an ANSYS presentation in 2009, and we can see that in a simulation of an extrudate, we can see that if we apply a certain amount of slip in the process, the output shape and form and dimension is completely changed by this slip parameter. So we can see in the bottom graph or shape, depending on the quantity of slip, we have a very, very large difference in shape. This is essentially, this slip coefficient is amongst other, based on the Navier's law, which is actually the tangential force as a function of speed as a power law of the slip velocity. So in 1931, 1932, the first method for wall slip measurement and correction was proposed by famous Melvin Mooney. So basically what he said is the total output of a capillary rheometer is the sum of the output in no slip conditions and the output in slip conditions, because we have most of the time, and especially with rubber compound, a mixture of the two. Since the apparent shear rate is given by 4 times the output divided by pi over pi times r cube, we can then use that in the previous equation, then rearrange to finally get the apparent shear rate equals the no slip shear rate plus 4 times the slip velocity divided by r. So this is a linear function, and at constant stress, if we plot that as a function of 1 over r, the slope will be equals to 4 times the slip velocity, which is the important parameter we're looking for, and the intercept is the no slip shear rate. Again, this requires 2, preferably, and we can see here, 4 times the test. Unfortunately, when people have tried to use the Mooney method on rubber compound, well, actually they found this in the graph where the no slip shear rate becomes negative. That, of course, is a complete nonsense, technical nonsense, and many compounds have been found like that. So some correction, some additional work was necessary. Later, 1989, or let's say late 1980s, early 90s, 2 persons have been working. I'm not going through the math. Everyone can have a look on the reference. But basically, Kalman Geiger proposed an exponential rather than a linear response for calculation of no slip or slip velocity and no slip shear rate. And that, of course, solved the problem of negative values, predicted values of no slip shear rate. And Vigrev proposed to a linear relationship, but with the inverse of the square of the radius. So in the case of steady shear viscosity, closed boundary cone, so RPA measurement, in standard plate, cone plate, open cavity machines, we do have a continuous rotation of the bottom plate, and we measure the torque on the top plate. This actually works very, very well with low viscosity thermoplastic, but does not work for rubber compound. So the stress calculation in that case is simply 3 times the torque divided by 2 pi r cube, r being the radius of the die. And the true viscosity is the ratio normally between the stress and the shear rate, where the shear rate equals the angular velocity divided by the cone angle, as we can see below on the left. So what is important is that in an open cavity, if you have a highly elastic and high viscous material, you're going to have no pressure inside the cavity, so you have slippage and edge fracture. In a closed cavity, edge fracture disappears, and you normally work under 50 to 60 bar internal pressure, completely eliminating slippage. Of course, we use groove dies. So programming a step strain, we can measure transient and steady shear viscosity. And when we look at stationary shear condition reach, we have steady shear viscosity. But it requires programmable strain, which is higher than pi, so meaning something like 2,500% and even better. Of course, that is important because the RPA then is able to measure both steady shear and oscillatory shear viscosity in one single instrument. So how it's done, it's very simple actually. You program a certain amount of strain at a given time, and the bottom die will move to the target elongation or strain in the program time. So it's very easy. Shear rate is in that case equals to gamma 0, which is the maximum strain divided by time. So if you want to program 1 reciprocal second in case of 1000% strain, is just a time of 10 seconds, which is really short. If you go to 1 turn, which is 2 pi, then it's going to be 50 seconds. And then by varying the time, you can change the shear rate. The response will be as seen on the left graph, where you have the first part of the graph, which is the transient shear, until you reach a stable stress, which indicates stationary conditions. Dividing the stress of the plateau by the shear rate gives you the viscosity. So the first one was done on a pure polymer. Now we are going to do the same thing on a thread compound, truck thread compound, with 4 different shear rates, and we are able to measure easily or calculate easily the viscosity, which can be plotted on the same graph of a capillary rheometer. And we can see that we have an extremely good correlation between the capillary and the steady shear viscosity on the RPA. One thing, there is a slight difference between the corrected viscosity and the apparent viscosity. So there is still a little bit of improvement to be achieved. So how we can do now look for wall slip in the RPA. So what we do is using groove dies upper and lower at high pressure, we are in no slip conditions. If we replace the upper die by a grooveless, so no groove, but mirror polished die, which is going to provide slip, but we have no measured the residual roughness of the so-called mirror polished die. So we do steady shear program with variable shear rate under pressure, and we can even vary the closing force in order to study the wall slip dependency to the internal test cavity. So it's another property we can measure. So the attempt for quantification of wall slip, we have to consider that we have a pressure-driven flow, which is a capillary rheometer, an extruder, and so on. So in the picture here, we can see that we have a die line. When we are pushing the Newtonian liquid through the tube, we're going to have a very nice parabolic because it's a line, because it's a Newtonian fluid. And at the injection point, we can see that actually the liquid hasn't moved. So there's no wall slip in Newtonian slip flow. In that case, we can see that actually the line has started to move away depending on the shear rate. Now, this is extremely difficult to see on a capillary rheometer with rubber compound. In drag flow, so plate, cone, plate, like RPA, especially on an open cavity, you can draw a line on the 2 dies and the material, and you're moving one die to one direction, and you can see that if the inner line on the material is tilted, that means you have some deformation of the material, therefore shearing. Now, at the bottom picture, if you have a straight line, vertical line, that means on both sides you had 100% slip, therefore everything moved as a plug. So now what we do, we take a compound, we test first at the range of shear rate the viscosity with groove dies, so we have no slip, and then we change the upper dies and we measure in slip conditions. So this is the variation in slip. This is a high slip compound based on EPDM. So we repeat now with the truck tread compound. We can see that we still have slippage, but in a much lesser extent, and that's quite normal. NRBR compound tends to slip much less than heavily loaded by oil and filler EPDM compound. So now, using this machine, we can define an alternative method based on some work which has been made in the CMF in south of France. So basically, using the Mooney slip velocity, they propose that the slip velocity is basically the difference in output in apparent output, so the total output minus the output from no slip condition. But of course, in that case, you need to know that output, and the slip velocity is therefore a multiplication of the shape factor multiplied by the difference in shear rate, apparent, and no slip. Of course, you need to know that, and this is an illustration of this analysis. Of course, you need to measure that at constant stress. So how to do slip calculation? So first of all, we're going to look at a very simple one, which is a linear system. So if you move the upper die to a certain position at a given speed, this is your apparent velocity. If you have put a mark, a line, then you're going to see that the first part is going to be the no slip velocity, and the difference between the two is going to be your slip velocity. Now, of course, in a cone-cone geometry, we are using a rotational shear, but the system is the same. The angular velocity in slip equals the difference in angular velocity, apparent angular velocity, minus the angular velocity without slip. And we have both that in the RPA using polished die and groove dies. So then, since the shear rate in a cone-cone machine is equal to the angular velocity divided by the cone angle, then the angular velocity equals the cone angle multiplied by the difference in shear rate. We can transform that into a linear slip velocity by multiplying by 2 pi at r. So what we can do then, we can plot shear stress as a function of shear rate. We're going to apply the Ostwald-de Waal model, which is the power law model. We're going to calculate the consistent parameter K and the pseudoplasticity index. There are two things here which are important. First of all, we see that the consistent parameter is going down for both compound, tread, and EPDM, much more for EPDM, of course, but also, which is important, in the plasticity index is increasing in slip condition compared to no slip conditions on both compounds. So now, by just measuring the difference in shear rates at different and constant shear stress, we can then plot or calculate the slip velocity. So the slip velocity is in that case measured here, And we have, of course, a high slip velocity on the EPDM compound, and much less on the truck compound. They both follow the Navier coefficient because it's a power law for both. It's a log-log scale. What is also interesting is that the slip ratio, which is the slip velocity divided by the apparent velocity, is actually decreasing when we increase shear rate and shear stress. And in the case of the EPDM, we can see that we reach almost 100% slip. And when we look at the right graph, we can see that actually in the no slip condition, the EPDM show a yield stress of about 30 pascal second. In that case, the viscosity goes to infinity, so the material can only move through 100% slip, so as a plug. Now, for the SBR-NBR industrial compound, we have measured no slip conditions on the RPA, and also a compound as such with biconical rotor variable speed Mooney. And we can see that both Mooney and no slip viscosity on the RPA are fitting very, very well. Although the corrected capillary viscosity is just following at low shear stress or lower shear rate the same path of the slip. So in that case, slip was really quite important. And again here, slip velocity as a function of shear stress, we can see that, and it was a little bit of a surprise. Actually, we have a dual response or dual Navier coefficient. I'm going to skip the effect of pressure because of time, so I will go a little bit quicker, but we can study that. This is just the graph to show you that actually the slip velocity is increasing when you are lowering internal pressure. So just for conclusion, the RPA with a ramp or steady shear test is a very efficient tool and flexible tool for measurement of both transient and steady shear viscosity of rubber compound. It has been really designed for that. Available shear rate range covers from very low to medium values, but it covers almost 5 decades of shear rate, which is not too bad. And it does not require lengthy or correction, such as in the capillary rheometer. The technique is therefore able to realign capillary rheometer data for study at high shear rate if necessary. The installation of polished dies with variable instrument cavity pressure offers a unique and extremely simple combination to study wall slip in rubber processing. And actually, it's really very, very efficient because the complete study takes only half a day for the wall slip measurement. It's the only available instrument able to separate shear stress rate and pressure effect in wall slip. That is not possible on a capillary rheometer because it's the difference in pressure which give us the shear stress. So the RPA, as I believe, steady shear viscosity measurement with slip and no slip paves the way to a deeper understanding of rubber compound flow behaviors, thus potentially improving flow simulation predictions. Thank you for your attention.